So last time we discussed the formation of the solar system and the different types of planet that resulted from the formation, such as terrestrial planets and gas giant planets. What we're now going to do is move into talking specifically about the planets themselves. And we're going to start out by going from the center of the solar system to the outside. So starting not with the sun, we'll discuss stars in their entirety later, but starting with Mercury as a planet and moving our way out until we've gone all the way out, yes, to Pluto. Even though there's controversy, we're going to go all the way out to the solar system and cover comets and asteroids on our way. So we are going to start with Mercury. What we're then going to do is talk about Venus and Earth in one go. These are two very similar planets apart from the atmospheres. Then Mars, and then we'll look at the asteroid belt, and then we'll move on to the subject of the gas giant planets. So we're really looking at chapter 7 here, talking about Earth and the terrestrial worlds. I'll try to point things out from the book, but generally I'm just going to go through each planet in turn and talk about some of the key features. So here are the planets we're talking about. These inside planets, these terrestrial planets, everything from Venus out to Mars. So we'll start off with part A, which is talking about Mercury. And we'll come to talking about Mercury and the probes that have visited it as we go, but if you look at this particular map, this was the best map we had of Mercury for a very long time. And as you can see, there's a chunk missing out of this map, and I'll explain why shortly. So let's put this into some historical context. So why is it called Mercury? Well, Mercury was the Roman version of the Greek god Hermes, and this is the guy over here with his little winged shoes and little winged hat, which was a little more than just a fashion statement, but enabled him to fly and travel at great speed. So the Romans basically assimilated the Greek gods into their own beliefs, and the Greek messenger god, Hermes, became Mercury. And he was the god of speed, god of finance, god of commerce, and because Mercury moved quickly across the sky, that's how it got its name. So the planet Mercury, being fast, got the name Mercury, the god. So Mercury, let's take a look at Mercury as we know it today. High surface temperature, 360 degrees Celsius. That's because it's very close to the sun. I'll discuss the temperature contrast shortly here, but as we can see here, the temperature on the night side of the planet, obviously the planet is going to rotate, temperature on the day side is 360 Celsius. The temperature on the night side becomes negative 140 Celsius. You can see it has a very large core compared to its mantle. If you look at the Earth, the mantle is actually quite thick, but the core, in terms of Mercury, constitutes most of the planet. And here it is in the center. The core is also a very intense iron. A lot of iron present in here, and that creates quite a large magnetic field for a body quite close to the sun. We can see plains, we can see cliffs, craters, lots of craters, and basins. And with Mercury, remember, one solar day is about 176 Earth days. So one day on Mercury is a long time in terms of Earth days. So in terms of observing Mercury, people really only saw it as a very bright star in the sky for the longest time. Then during the 1970s, the Mariner probes attempted to send a probe to every planet in the solar system. As you can see, this actually looks like an upside down wall-E with little arms and solar panels. And this was the Mariner series of probes. Mariner 10 was sent to Mercury. And as we discussed orbits earlier, this was a sort of hyperbolic slingshot orbit, and it shot by Mercury and photographed Mercury as best it could on the way by. It's actually a slingshot from Venus, so it had a gravitational assist from Venus, converted that gravitational potential energy to kinetic, and picked up speed, and shot by Mercury really quick. It was then the only probe to visit Mercury until Messenger went back in the 2000s. So the map that was created in 1974 was the best map we had until 2013. So Mercury is so close to the Sun, it was difficult and energy inefficient to go into orbit. So the Mariner 10 probe passed by Mercury twice, once on September 21st, 1974, and again on March 16th, 1975. Unfortunately, the timing of the flyby was pretty poor, and by the end of the mission, Mariner 10 only mapped 45% of the surface because it kept imaging the same places. So we only had a 45% map of this planet up until a couple of years ago. So Messenger, the last probe that we've sent to Mercury so far, means the Mercury Surface Space Environment Geochemistry and Ranging Experiment. I think NASA actually has a department of acronyms that comes up with these things. The total travel time before getting into orbit, because it actually did go into orbit this time and not just shoot by, was about 6.5 years to get there. And here's a nice image of the Messenger probe coming into orbit above Mercury, getting ready to do its mapping orbit. And there we are. So what you're seeing here is the Messenger probe in orbit around Mercury with its various sensors and cameras, and splitting the planet up into grids, and then what will happen is the spacecraft will sweep by in an orbit from the poles, and it'll sweep down and slowly image the entire planet. And that's exactly what we got. After nearly 40 years of seeing the same images, we finally got a complete global map of Mars from Messenger. And this is what it looks like. To most people, it looks like the moon. There are quite a few differences. If you look at pictures of the moon, we'll talk about the moon later, there are mare or seas, large dark areas, much darker than this, which are kind of absent on Mercury. But it really is very moon-like, sort of grey, basaltic sort of colour to it. The reason these craters appear deeper is because the illumination angle at which they are actually photographed. One of my expertise is orbital imaging of planets. So obviously there's a bit of distortion here. That's because this is really a spherical map that has been stretched out into a cylinder, so you can see the detail in a square sense rather than looking at it as circle. So hence the sort of deformation of the image at the top and bottom. But here it is projected, and this is our complete map of Mercury so far. As you can see, these blasted ray craters down in the south. One of these is Caloris Basin, which we'll talk about shortly. So there are a number of problems when people are looking at Mercury. Why is the planet so dense? What's Mercury's geological history? The structure of Mercury's core. Mercury has a weird magnetic field, very strong considering the position of this planet. And it also has kind of unusual materials at its poles. So in terms of impact cratering, one of the main features of bodies that don't have a lot of weather is impact craters. The Earth has been hit many times by craters. It's just that we don't see those craters because there has been geological resurfacing, lava flows, there's been rain, there's been wind that have weathered the craters and taken them away. If you're looking at planets like the Moon or Mercury, then you see a lot of craters because there's no weather there to destroy them. So craters are one of the main features of Mercury and are found pretty much at all latitudes of the planet. They're far more spread out than the Moon. As we said, with the Moon there is some infilling. There are mare, there are seas, there are lava. In this case, the craters are quite far apart. Here we're looking at a 200 kilometer range scale, and in this range there's actually areas where there's quite a large spacing between comets. The largest surface feature starts here, and this is referred to as Caloris Basin, as I said before. And this was discovered by Mariner 10 in 1974. And the basin was basically on the terminator. Remember the terminator being the division between the day and the night. And the probe flew by and imaged it. I say here that the only 50% of the crater has been seen. That's not true anymore, because basically Messenger has gone by and imaged this since. But at the time when Mariner 10 saw it, only 50% had been imaged. So it's 1,300 kilometers across, and it's ringed by 2-kilometer high mountains. And here's the image that was so famous. Yes, that's all they could tell from. But you can go back to the other images and you can find it. The impact crater, here's a better picture of it, is basically half of Mercury's radius. The basin is enormous, and it was formed by an enormous impact. And then the crater floor is filled in by lava plains, similar to the way we have what are referred to as maria on the moon, or mare. The ejecta, which is the material thrown out from the crater, actually covers about 100,000 kilometers there. And the impact was large enough to give you a ring pattern that formed all the way around the planet. Now, caloris, as it sounds, is very similar to the unit of the calorie, and that's because they both come from the same name, and that is the name meaning the word heat in Greek. Caloris, it means heat. And the reason it's called Caloris Basin is because it's the hottest place on the planet. This part of Mercury is pointed towards the Sun every second perihelion. So it's actually, as far as direct solar heating goes, this is one of the hottest places in the solar system. There are hotter places due to atmospheric or geological effects, but this is the hottest part of Mercury, the hottest part anywhere, just due to sheer solar heating. And there's a pretty picture of a giant impact forming Caloris Basin. And there's some of the terrain in Caloris Basin from Mariner 10. Very cracked, very heated. Remember the actual rocks on Mercury, they're heated to an enormous degree during the day, and they're cooled to an enormous degree during the night. Which means there's lots of thermal stress on the rocks that can crack them and cause some weathering, even though there's no direct weather as such. It can cause fatigue and cause them to break. So this basin is just slightly north of the equator and is south of what's really referred to on the planet as weird terrain. Yes, that's what it's actually called. I'm not just saying this is weird. So the basin's just south, and its opposite side of the planet to this weird terrain is crumpled hills. Now, weird terrain is formed because when a planet undergoes an impact from a large body, the shock waves have to go somewhere. Remember, energy has to be conserved. So the kinetic energy travels through the planet in the form of seismic waves, and then bounces through the core, out the other side of the planet, and cracks the other side of the planet. So this weird terrain is a result of the shock waves from the impact that formed Caloris Basin travelling through the planet and cracking the other side. And this is the weird terrain that you can see, these undulating, cracked hills. And there's another shot of it. So basically Mercury is very sort of dead, sort of moon-like world. It's believed there are some outgassings coming from beneath the surface, but very little. No weather activity. All of the atmosphere has been stripped away by the sun. The solar wind has taken away or any gases that were once around this planet. So tectonics. We have plate tectonics on the Earth. These are the seeming movement of rocky material floating on rafts of lava on the Earth. Tectonics in Mercury seem to be different than tectonics on any other planet, and they've created enormous cliffs that are called scarps. And this is when tectonic forces basically compress the crust of the planet and cause the surface to crumple up. So it might indicate that parts of the surface are actually shrinking. And this might be gravitational. It might be also thermal stress effects. So this is what we're looking at. At some point, Mercury's core and mantle shrank down, and the actual outer skin stayed the same. So this is akin to the kind of people you see where they undergo rapid weight loss and suddenly have a lot of excess skin to deal with. This is the kind of thing that really happened to Mercury. So what happened with Mercury is it had a lot of weight in here, and the Mercury's core and the mantle shrank down, and it caused the entire crust to contract, and its excess skin started to hang off in folds. So the crust slid over other parts of the crust, and that gave us what we see here. So what we're seeing here is this is a very old crater formed here, and then part of the crust, part of the outer skin of the planet, has slid over this part of the outer skin of the planet, and it's given you this disjointed kind of line. And you'd be kind of forgiven for thinking maybe that was an artifact of the image, but it isn't. This is actually tectonic activity on Mercury that's disrupting the outer surface of the planet. So, in terms of scientific parlance, scarps are caused by land displacement due to movement along a fault line. These things happen on Earth, but not the same as Mercury. They're very localized on the Earth. On Mercury, we see these fault lines running for quite a large part of the planet. Some of the Galilean moons, remember Io, Europa, Ganymede, and Callisto, show very similar tectonic activity as the Earth. So does Titan. So Earth is not alone in having plate tectonics, we don't think. But the system on Mercury is a little bit different, as I said, due to the overall bulk shrinkage of the core. And here's another fault line running through this system of craters. See where this has seeped. This part of the crust has seeped over this part. And it's actually accentuated the edge of this particular crater, this lip on the crater. Same here. This is an image artifact, ignore this blur. This is blur caused by the relative spacecraft motion being wrong relative to the rest of the image. And as you can see, here's that crack again. There is some evidence of volcanoes that once existed on Mercury. There's evidence that some of these craters were formed by impacts and then were backfilled. They were filled in by lava afterwards from craters. Sorry, from volcanoes, I should say. So the craters were filled in from volcanoes. So Mercury, it's believed, once had similar volcanic activity to our own moon. A lot of the surface of Mercury seems to resemble the moon. And this is the kind, if you would be forgiven for thinking this is the moon in a close-up, because this is the kind of material and the kind of landform that we see when we look at the moon. So Mercury and the moon seem to have similar geological activity. And there's a picture of it, pretty blasted with craters, lots of holes, very rugged world. Very hot, no particular atmosphere to weather these craters. The only weathering is thermal effects from the sun, and the fact that you are heating and then rapidly cooling these rocks, and the possibility of some weathering due to the scarps that we looked at, and due to the tectonic stresses of the planet. So as far as Mercury's interior goes, its core is extremely dense. It's almost a pure iron core. The outer crust and the upper area of the crust, the actual sort of what we would call the surface soil, the lithosphere, is made of pretty light silicate with some iron. As far as we know, Mercury is today geologically dead to all intents and purposes. The planet itself is very small and can't generate enough tidal force to get internal heat going. So part of the gravitational interaction between the Earth and the Moon generates geothermal energy within the Earth. Mercury doesn't have a moon and was probably geologically active at its formation, and that activity has died away. So any outgassings from Mercury or any volcanic activity we have today is just remnants, and very little has been seen, at least nothing by space probes. And here you can see the lithosphere, and then we've got the mantle, and then we have the core of Mercury. And here's a nice comparison of the Moon and Mercury together. As you can see, very similar colouring, very similar materials. This is the Moon, this is Mercury. The Moon has these larger mare, these larger what we refer to as seas. Seas basically being large lava-filled basins, which, although Mercury has these, they're nowhere near the extent, the percentage coverage of Mercury's surface as they are on the Moon. In a surprising turn, the magnetic field of Mercury is actually quite strong. It was actually believed at one time that you would need a lot of geological activity and rotating liquid metal in order to have a magnetic field. We think Mercury is geologically dead, yet it has an actual powerful magnetic field, and the magnetic field is very similar to that we see on the Earth. It's also surprising because, as I said, magnetic fields are generally generated by rapidly spinning metals. Mercury's axial rotation, its day length, is actually extremely slow. So the actual generating mechanism of the magnetic field is relatively unknown. It may actually be just locked into this enormous magnetic iron core. So the interaction of Mercury's magnetic field and the Sun make for some really interesting physics. You're talking about a star which has a significant magnetic field with a planet very, very close to it with quite a strong magnetic field itself. And as Mercury goes around the planet, as Mercury goes around the Sun, the planet punches a hole in the Sun's magnetic field. So Mercury's magnetic field is strong, and it's passing through a big, strong magnetic field. And that actually creates some really interesting physics. So as we said before, there's a large number of craters on Mercury's surface, and that suggests that Mercury has undergone very little crustal modification. That means there hasn't been much volcanic activity on the surface of the planet for a very long time. Now, as I said, the molten dynamo effect is the effect where we have liquid metal spinning around inside a planet. Well, if that causes magnetic fields, well, Mercury shouldn't have one because it's geologically dead. No tidal interactions. So the magnetic fields are caused by this molten dynamo effect, but we don't see that effect on Mercury. There's no crustal modification, so there's been very little actual geological activity. So we're not really sure why Mercury has the magnetic field that it does, other than I said before, that it could be locked into a very powerful magnet at the core that came from its formation. But here's the kind of effect you have. The solar wind and the magnetic field of the Sun blasts outwards and hits the magnetic field of Mercury, and that pushes the magnetic field strongly backwards. So it's not a symmetric magnetic field. Anyone who has taken a magnet, put it under a sheet of paper and thrown iron filings on that paper can see the shape of the magnetic field. And I'll actually try and show a video of this for you. Now, that magnetic field that you'll witness if you conduct that experiment is symmetric. In the case of a planet's magnetic field, it should be symmetric in the same way. But the magnetic field and charged particles from the Sun creates what's called a bow shock and pushes the magnetic field of the planet backwards and makes it all extend outwards away from the Sun. So here's MESSENGER, the probe, and it's coming into and out of Mercury's magnetic field in order to orbit it. And that really makes for quite interesting physics for this little probe as it comes into an intense magnetic field and then out of it while it's already in an intense magnetic and electromagnetic field from the Sun. In terms of Mercury's orbit, it is the most eccentric of the major planets. Its orbit's inclined by 7 degrees to the ecliptic, which is a little more than most of the other planets are, with the exclusion of the non-planet candidate Pluto these days. And Mercury's distance from the Sun ranges from about 46 times 10 to the 6 kilometers to 70 times 10 to the 6 kilometers. One Mercury year is about 88 days, Earth days. But because of its orbit and its weird day to year length, if you could actually stand on Mercury, you'd see some weird things. I'm not going to test you on this particular slide, but I'm just going to point out this whole day to year length ratio. If you're standing on Mercury, at certain points on Mercury's surface, you would see the sun rise. It'd get about halfway in the sky, reverse direction, and then set, and then rise again, all in one Mercurian day. And that's really because you get about 4 days prior to perihelion, the angular orbital velocity is going to be equal to your rotational velocity. So the apparent motion of the sun actually stops. It's very strange effects that you would have if you could stand on the surface. At perihelion, the angular orbital velocity exceeds the rotational velocity, so the sun appears then to move backwards. And in 4 days after perihelion, the sun's normal motion resumes. So what that means is it comes halfway, changes direction, then sets, then rises again. And remember, the day length is extremely long. We kind of discussed precession of orbits previously, and the slow precession of Mercury's orbit around the Sun was seen in the 19th century and couldn't be explained by Newtonian mechanics. We needed general relativity and Einstein's work to explain Mercury's orbit fully, because Einstein's theories explain the effects of very intense gravitational fields. Getting obsessed with magnets. Einstein's work explains the effects of intense gravitational fields. And Mercury is so close to the Sun that you need general relativity that didn't come along until the early 1900s to explain these effects. So when they were making observations in the 1700s and 1800s, Newtonian mechanics did not because they couldn't explain the orbit of Mercury, they actually invented a planet called Vulcan that was thought to exist inside the orbit of Mercury that was even closer to the Sun. If you put this planet inside Mercury's orbit, it would actually account for the weird perturbations of the orbit. So now we know that general relativity is required to understand Mercury's orbital precession. So the effect is actually quite small, but was discernible by people with Newtonian physics. But now we put a relativistic correction in there and look at the movement of Mercury at its perihelion point, we can see that it moves about 43 arc seconds per century. Remember, an arc second is 1/60th of an arc minute, and an arc minute is 1/60th of a degree. So it turns out that once we ended up with general relativity and we explained the gravitational effects in terms of relativity, we didn't need to have this planet Vulcan. So if anybody watches Star Trek, we're talking about a real planet that was actually theorized to be called Vulcan, and nobody with pointy ears living on it. If they were, they'd all have been incinerated. So occasionally you'll see pseudoscientists refer to this planet. It doesn't exist. This was an effect of relativity we didn't understand. So in terms of atmosphere, as I've mentioned before, it probably had some primordial atmosphere. That was gases that the planet itself actually trapped and held on to for a short while after it formed. That atmosphere would have dissipated very, very quickly after the planet's formation. The planet has very low gravity, very high temperature, and the intense charged particles, the solar wind from the sun, would have stripped the atmosphere off and basically destroyed it. There are traces of a really, really, really tenuous atmosphere around Mercury. Hydrogen, helium, a little bit of oxygen, sodium, calcium, and a bit of potassium. but the pressure level is about 10 to the negative 15 bar. On Earth we have 1 bar pressure, so we're talking 15 zeros on top of Earth's particular atmospheric pressure. So very, very tenuous, if you can even call it an atmosphere at all. Just remnant gases would be the way I would refer to it. In terms of weather, well, as I said, there's no real atmosphere, so there's no real weather on the surface of Mercury. So what you're really talking about in terms of temperature is temperature changes due to the effects of direct solar heating. So temperature variations in any bodies without atmospheres or extremely weak atmospheres are really, really pronounced. So this is something that will happen not just on Mercury but also on the Moon. This is also a problem for things like spacecraft and people who wear spacesuits, in that the shade has a very low temperature and the parts in direct solar illumination have very high temperatures. So if you take a look at something like Mercury, during the day you can have temperatures of up to 420 Celsius. At night you can get to negative 180 Celsius. And those changes will give thermal stresses on the surface. Rocks can be weathered and cracked based on the extreme heating and extreme cooling. And remember that there's no real weather effects here. There's no atmosphere to speak of. It's just real solar heating that causes these rocks to be cracked and undergo stress. So bodies with little to no atmosphere don't have the normal heat transport mechanisms that we have. Convection moves a lot of heat energy in the Earth, or I should say in the Earth's atmosphere. So anyone who's experienced turbulence in an aircraft, that is basically rising gas being hot and sinking gas being cold. And that convection moves energy around in our atmosphere, moves heat from place to place. Without those effects, you're really just dependent on brightly lit areas being hotter than colder areas. And you can have very, very high contrast effects. The only heating comes from the sun itself. So temperature variations are basically based on radiative heating. So brightly lit areas can get to 420 Celsius. Areas that are in a shadow can get down to negative 180 Celsius. And they can be literally inches or centimeters apart from one another and have this enormous temperature contrast. So if you're a rock that's about 30 centimeters or a foot long, then part of your rock can be in shade and part of that rock can be heated. So part of your rock can be held at 420 Celsius and part at negative 180. And that's an extreme temperature differential for one body to experience. So bodies with little or no atmosphere don't have convectional effects, and that requires some gas or liquid. And if everything's based on radiative heating, the temperature in areas with direct sunlight can be up to 400 Celsius, and the temperatures in the shade to negative 180. Much more extreme than planets with an atmosphere. So no convection means the temperature difference between light and shade is very extreme. So if we take this particular picture of Aldrin on the Moon, now there are very few pictures of Armstrong himself on the Moon. I know we're switching to the Moon here from Mercury, but they both have the same mechanisms in play. So what we're dealing with is sunlight and dark. And I'll go back to what I was saying. I diverge a little. This is a picture of Aldrin on the Moon. People think it's Armstrong, but it isn't. Around about the time they were due to switch cameras so that Aldrin could take lots of pictures of Armstrong, the president phoned and they didn't have time to switch cameras. But Armstrong is in this picture. If you zoom in on Aldrin's faceplate, there's Armstrong taking the picture of Aldrin. But this is Buzz Aldrin. Anyway, that was a complete aside. What we were talking about was weather and temperature, or the lack thereof of weather. So here we have an illuminated part of the Moon, And here we have shade, the shadow of Buzz Aldrin on the moon. Here in the sunlight, it's 127 Celsius. Here in the shadow, it's negative 173 Celsius. And that's a space of just a few inches from here to here, because there's no convection. And that's the same as it is on Mercury. Mia, don't. I need to do that.